Konstantin Avrasenko is there, Lasse Leskilä is there, and Vinay Kumar, who unfortunately couldn't make it into this conference. Yes, the work is on multi-layer hypergraph clustering using the aggregate similarity matrix cluster of words that you'll hopefully be familiar with after this talk. So this is the structure of the talk. I will motivate our work, introduce the statistical model we use, and then discuss the community recovery problem. So as you heard in the first talk of the day, hypergraphs actually capture multi-way interactions, whereas graphs tend to capture two-way interactions. And there are many examples, such as was discussed, capturing the communities of authors based on their research output, for example. But here I will discuss example of table reservations in restaurants. So imagine that you have two groups of people who prefer pizza and those who prefer pasta. This set of people is the node set, and the table reservations are the hyperedges. And in this example, each hyperedge has 4 nodes. So this is a uniform hypergraph we discuss. And multi-layer hyperedges actually capture interactions of different types. So in this previous image, this is a single layer, so single hypergraph. But if we have, for example, have multiple restaurants, those can be modeled as multiple hypergraphs, and they in total form a multi-layer hypergraph. And now to the community recovery problem. So imagine that there's some underlying process. In this case, pizza and pasta lovers might navigate towards different restaurants, maybe prefer eating with other pizza lovers and pasta lovers. And based on the hypergraph, we would like to recover the communities of these individuals. So to generate these hypergraphs with community structure, we first specify a model parameters. So there are n vertices in 2 communities, which we denote by -1 and +1. There are m layers, restaurants in the previous example, and d vertices in every hyperedge, which makes this a uniform hypergraph. Step 1, we sample the community structure. From uniformly form the set of all community structures with equal number of +1s and -1s. So this is a bisection of the node set. And step 2, for each layer M and for each set E of D nodes. So this is a potential hyperedge. We observe the hyperedge with probability B as shown here, and we won't observe it with probability 1 minus B. And we hope to encode the community structure to these parameters B. So together, these A here form a so-called hypergraph incidence matrix. This is not the exact incidence matrix that was discussed in the earlier talk, but instead, as you can see, it parameterized. It's indexed by edges and layers. Yeah. And now to the probabilities of observing a particular hyperedge. So the hyperlink's probability depends on its community profile. And in what is a community profile? We essentially count the number of nodes in node set of size D belonging to communities -1 and +1. So both of these node sets have a community profile of 3, 1, even though a different node belongs to the blue community or +1 community. Or I think I had the indexes other way around. Yes. And now the link properties are characterized by these community profiles. And now to the scaling regime. So we take the logarithmic average degree regime. So these alphas here are constant, independent of the number of nodes in the network, and this takes care of the scaling. And this is also the regime where the phase change for the connectivity happens. And finally, we assume symmetry. So these class labels don't affect the community probabilities. So sorry about that. Yes. So you could imagine that changing the blue ones and red ones around here wouldn't change the parameter. Yes. Why?
Why do you assume this?
We assumed this specifically because it was easier, but this is discussed in the last slide of the talk. Now to the community recovery problem. So we introduce a similarity matrix with which counts the number of hyperedges a particular node pair appears in. So this is a helpful image. So take node pair. In this case, you could look at a pair of nodes A and C, and you observe that this node pair is simultaneously incident to this first and the second hyperedge here. So you have 2 in the corresponding element in this similarity matrix. This is a single layer case, but if we have multiple layers in the network, then you just aggregate over the layers. That's where the name aggregate similarity matrix comes from. You do that for all node pairs. And now we aim to recover the communities from this aggregate similarity matrix. So why is that? Firstly, it takes a lot less space to store the aggregate similarity matrix instead of the full hypergraph. Secondly, somehow this might reveal some unwanted aspect of some person's behavior, so you might want to preserve some privacy and instead give researchers the similarity matrix instead of the full information of who they dine with and where, so for example. So the data is sample. Yes?
So why would you aggregate those matrices? Because I think it would be exactly useful not to aggregate them if you have this multi-layer hypergraph.
Yeah, so here we assume that the layers are independent.
Okay, so it's not that pizza lovers and pasta lovers, and one is pizza restaurant and the other is pasta restaurant, but that's restaurants, right?
Yeah, they might have different link probabilities, but they're independently sampled from some hypergraph stochastic log model. Okay. So yes, you might want to look into different ways of doing this, but at least if there are tons of layers, the aggregation saves space again. So that's interesting to know what you can recover from this aggregate data. Yes, so this is the data. So we're specifically observing the similarity matrix instead of the full hypergraph. And we want to find an estimate of this underlying community structure sigma, this sigma hat, that exactly recovers the communities. And By this I mean that the probability of estimating the correct community structure should approach 1, and this plus minus here just somehow resembles the best we can do under our assumption of symmetry. So these two community assignments, sigma and minus sigma, represent the same community structure. So it's the same bipartition of the bisection of the network. And one way to approach this problem is to look at the MLE, and it turns out that the MLE reduces to this cut problem. And what is a cut problem? So we have an input, the aggregate similarity matrix that you're now familiar with, and we have output, which is a partition matrix, which has element +1 in the so element ij is +1 if nodes I and j share a community, and -1 otherwise. And what's the algorithm? Okay, firstly I have to discuss a tiny detail that I will go into a bit later on. So if you have the assortativity, so if nodes who share a community tend to appear in more common hyperedges than nodes who don't, then we have to solve this maximization problem. So what this min bisection problem does is it just tries to gather the maximum number of +1s and as few -1s as possible. And it does that over all valid partition matrices. And this is equivalent to this quadratic problem here. So the constraint ensures that the community sizes are equal size, and we have the desired community labels. So this is the quadratic version of the min bisection problem. And this is unfortunately NP hard. So we approximate this using the SDP semi-definite programming. And this was first introduced by Kim, Bander, and Gomez, this particular SDP. And here you can convince yourself that the solution of the original one is also a solution to the second one by taking this. And now we're optimizing over the cone of semi-definite matrices X instead of these integer vectors X as in the quadratic problem. Okay. Now this is a disassortative case. So if nodes who don't share community are expected to appear in more common hyperedges, then you have to turn this maximization into minimization, and this sign change does that for you. And since we're looking at asymptotics, you have to be very careful about what this inequality here means. So essentially you have to normalize these to be independent of the scaling and then have some inequality. And now to our main result. So the SDP can indeed attain exact recovery. So this is the algorithm where this S reflects the desired assortativity. So in case of assortative data, we have the +1, and this assortative case -1. And when this data is sampled from the model and W is the aggregate similarity matrix of this A sample from the model, then under a particular assumption that I will discuss soon, we indeed get the correct partition matrix as the unique optimum of this program with high probability. And the information theoretic metric looks quite complicated. Maybe the proof outlined later on in this paper give you some insight where this comes from.
How do you solve the relaxation of the problem? Go to the actual community structure for this? Is it just round or when you?
Sorry, now I did the same.
Yes, I've done that a few times.
What do I have to do? Control L. Thank you so much. So if so this is asymptotic. This is the asymptotic result, and if the relaxation attains this sigma transpose, it is also a solution to this original. Yeah, you go backwards. It's also a solution to the original problem. Yes. So now to the proof idea. So if you have dealt with programming of any kind, you might be familiar with primal and dual programs. And our primal problem here has the following dual problem. And what does how do you derive the dual problem is basically you look at, you penalize breaking of these primal constraints here, and you somehow try to find lowest possible non-trivial upper bound for your primal objective. So you end up with something like this. This S here is our dual constraint. So this particular matrix has to be positive, semi-definite, and this D and nu are our dual variables. And weak duality does what stands here in the headline. So recall the definition of the probability inner product. You start from the primal objective. You use the definition of this S here in the dual constraint. You expand by linearity, and you use this primal feasibility here, and you end up with your primal objective being upper bounded by this dual objective, since this inner product here is positive. And we use this weak duality to derive a sufficient condition for optimality of our desired solution. So this partition matrix here, as I said, element ij is +1 if the nodes I and j are in the same community and -1 otherwise. So this reveals you the community structure. And this here is optimal if, since our primal is always upper bounded by a dual, so if this is 0 and these two are equal, it's the best we can do. And the uniqueness of this here can be established using one assumption that I will soon reveal. So if you take any x, which is not necessarily of this form, and you satisfy the sufficient condition above, then due to this positive semi-definiteness, you have the following. And since this holds, for any vector v, x times v is in the kernel of S. And when the kernel of S is indeed the span of sigma, and we have the primal feasibility. So we basically lock the diagonal of x as all ones. Then the columns of x are this true community structure up to assign change. And this lemma just gathers what I wrote here above. So suppose there is this diagonal matrix D such that the following conditions are satisfied, then we have our desired unique optimum. And now we have to check whether these conditions of this lemma hold. So we just guess and we find a good DII. If you were here last week, Lasse discussed these degree profiles. And what is a degree profile? We just take a node I and sum each node somehow so in adjacent to I if it's in the same community, and subtractive if it's in a different community. And now with this selection, it's easy to verify this that the sigma is indeed in the kernel of S, but whether or not it's the full kernel and this positive semi-definiteness here holds, we have to check. So this just reflects our desire of this kernel being one-dimensional. So all the rest of the vectors X should have strict inequality in this definition of semi-definiteness, positive semi-definiteness. How do we ensure this? So we hope to prove the following lemma. So let the expected aggregate similarity matrix be this expected X and W. Then for any X, we have the following. So this quadratic form here is lower bounded by this difference, and we treat these terms independently. So to treat the first term here, we need actually our information theoretic metric I, and let there exist some let the I be greater than 1, then there exists some constant epsilon dependent on these model parameters such that the probability of DII exceeding something logarithmic is approaching 1. What this says that the DII is at least a logarithmic with high probability, and so we should have this second term being smaller than the first term, and indeed this concentration inequality here ensures that with high probability this is less than the square root of the logarithm, and this m being the number of layers. And these two combined here ensure that something at least logarithmic at something minus something at most square root of logarithmic, you have strict positivity. And now to our summary. So we study the hypergraph stochastic block. Yes.
First proposition, you are working on I, right? And in the top, you are minimizing over I. So how does this minimization affect? So how do you go through proposition on the fixed I to the minimum over I to get the first part in the lemma?
So you have to show that the probability is somehow low enough that you can use union bound. Yes. Yeah. And this here is a Chernoff type inequality. So this this I arises from that. Yes. So we studied this hypergraph stochastic block model with multiple layers, and HyperEdge probability is based on community profiles. And we established that the SDP algorithm indeed recovers the true community structure exactly when this information theoretic metric is greater than 1. And our algorithm and result covers both the associative and disassociative cases, and instead of the full hypergraph data, we use the similarity matrix W. And for future work, we might want to look at asymmetric cases where indeed changing the labels, so red ones to blue ones or -1 to +1s would might affect the link probabilities. And you might also want to establish that our sufficient conditions are necessary or not, and look into non-uniform hypergraphs with different hybrid sizes. So that was all. Thank you so much.
Thank you so much. Any quick questions?
Yes, Martin?